So in this topic, we are given a random variable x and its probability mass function or probability density function according to whether it's discrete or continuous. And then a new variable y is defined as a function of x, that is some function phi of x. And because x is a random variable, y is also a random variable. And if x is discrete, y is also discrete. And we will consider cases where if x is continuous, then y is also continuous. So um, we will not consider functions like rounding off, for example, where a continuous random variable may become discrete. So we are going to consider discrete to discrete and continuous to continuous transformations. Okay, so this topic can also be called transformations of random variables. So we will look at one-dimensional random variables to start with. So the question is, if we know the PMF or PDF of x, the probability mass function, the probability density function of x, then given this function phi, how do we get the PMF or PDF respectively of y? So then the first case where x is discrete is actually the simplest case, and there isn't much uh, methodology required to get the PMF of y in that case. So if x is discrete, it has a PMF f of x, and in that case, the PMF of y can be obtained just by equating probabilities. So recall that the probability mass function is the probability that the random variable takes a particular value for all possible values. So in the case of y, its probability mass function, say g of y, is the probability of capital Y being equal to a given value, small y. And since y is phi of x, we can write that as probability of phi of x equal to a certain value y for every possible value of y. Okay, and since these two events are equivalent, so if you consider the event here, y equal to y is the event, and this is exactly the same event written in another way, and this we can find the probability of this in the usual way. So that will give us the probability mass function of y. So let's look at two quick examples. So here we have x with probability mass function f of x given in the usual way. You have x taking values -1, 0, 1, and 2, and these are the probabilities of those particular values. And for the same random variable, let's consider two different possible functions. One is y equals 2x plus 2. So y is a random variable, discrete obviously. And another is z equal to x squared. This is also a different random variable defined in terms of x as another function. So now in the first case, what happens is we want the probability mass function, say g of y, So clearly, if x takes values -1, 0, 1, and 2, what are the possible values of y? They must be 0, 2, 4, and 6. To see that, just substitute the values of x here. So when you put x equal to -1, y becomes 2 into -1 plus 2, that's 0. When you put x equal to 0, you get 2. For x equal to 1, that's 4, and x equal to 2, that is 2 times 2, 4, plus 2, 6. So these are all the possible values of y. Now, when you say, for example, g of 0, which is probability of y being equal to 0, in terms of x, what is that? Probability of 2x plus 2 equal to 0. But this event 2x plus 2 equal to 0 is equivalent to x equal to -1, because the only way that 2x plus 2 is 0 is if x is -1. Just solving this simple linear equation, x is equal to -1, and that is f of -1, right? So f of -1 is half. So that means the probability that y is equal to 0 is the same as the probability that x is equal to -1, and that is half. Similarly, y is equal to 2 only if and only if x equal to 0, and that one has probability 1 by 4. and here in a similar manner you get 1 by 8 and 1 by 8. So this is a very simple case. Now the other example where z is equal to x square, again, for all the possible values of x, what are the possible values of z? So if x equal to -1, then z is equal to 1. If x is equal to 0, z is equal to 0. If x equal to 1, again z is equal to 1. So that's already covered here. We don't repeat the value when writing the function, right? It's 0 is one possible value, 1 is another possible value, and when x equal to 2, z is equal to 4, that's another possible value. So these are all the possible values of z. Now what is the PMF of z, say h of z? So again, as before, we have h of 0 is probability of z taking the value 0, which is equivalent to x square taking the value 0, which is equivalent to x taking the value 0, and that is f of 0, which is 1 by 4. That's fine. Now similarly, what is h of 1? So you might have guessed that something different happens in this case. So here we have probability of x square equal to 1. So that is probability of x being equal to plus or minus 1, right? So there are two possibilities, x equal to 1 or x is equal to minus 1, and they are mutually exclusive possibilities. So probability that x is plus or minus 1 is probability that x equal to 1 or probability of x plus probability of x equal to minus 1, which is f of 0 plus f of I'm sorry, f of 1 plus f of minus 1, which from here is half plus 1 by 8. So that's 5 by 8. Okay, now for the last value here, this is easy to see. So I'll just quickly write the main point of it. So z equal to 4, that is x square equal to 4. So actually the possibilities are x equal to plus or minus 2. But x takes 2 with probability 1 by 8, and it does not take the value minus 2, or it takes the value minus 2 with probability 0. So the only possibility here is 1 by 8. Okay, and you can see that clearly these add up to 1. So this is correct. Also, another way to get this in this particular cases, you can just take 0 and 4, which are obvious, right? And the complement is this, because this is the only other possibility. So that is 1 by 4 plus 1 by 8 if you find, and subtract from 1, you will get 5 by 8. All right, so the discrete case is simple because you just have to use this, and the probabilities you can always equate because you have equivalent events here. The key point here is these events are equivalent. In fact, here they are the same event. So when you take the inverse function, when you write x equal to phi inverse of y, like here, phi of x equal to 0. So x equal to phi inverse of 0, which is minus 1, because phi of x over here is 2x plus 2. If phi is not an invertible function, so if z equal to x square, z equal to the square of x, which is not invertible. So when you take the inverse, you get multiple values. That's why it's not invertible. It's not 1 to 1. So here, even though we may say phi inverse of 1 over here with phi as x square, phi of x as x square, phi inverse is not actually one function but two different functions, or it gives two different values, right? So in that way. But anyhow, this is you can just enumerate the possibilities and compute the probability. What happens in the discrete case though? So let's take I'm sorry, what happens in the continuous case? Let's look at another simple example. Now we have, say, fx equal to 2x for x between 0 and 1, which is a valid PDF. If you integrate, you get x square from 0 to 1, which is 1, and it's non-negative. So this is a valid PDF. And let's say y is equal to 2x square. Okay. Now, what is f of x? It is the PDF, not the PMF, because this is continuous. So the PDF is it equal to some probability? No, it's not equal to any probability. Rather, it is the probability density. So actually, the probability is only given by the CDF. So if you find the CDF, which normally when the PDF is say lowercase f of x, then the CDF is normally written as uppercase f of x by convention. So this CDF is probability of x being less than or equal to x. Now this is a probability, and remember again, like over here, even here also, the only thing we can equate are the probabilities of equivalent events. There is no property that allows us to equate the probability densities. We don't know how probability densities work in terms of equating different probability densities. So we cannot do that, right? So the only thing we can do is equate the probabilities of equivalent events, and the only way to get a probability here is to use the CDF. Or you can find the probability of x lying in a particular interval, for example. That's also possible. But this is the simplest possible interval in a sense. And the CDF is a well-known function of the random variable, right? So I mean associated with the random variable. So we use the CDF. Now, this tells us that we may not be able to find the PDF of y directly, but rather we can find the CDF of y. So CDF of y, say capital G of y, if we are to take small g of y as the PDF, then this is also defined as probability of y less than or equal to y. Now this is a probability, and here indeed we can use this definition. So y is exactly 2x square, and remember this small y is a value, okay? Only capital Y is a random variable. So probability of y less than or equal to y is equal to probability of 2x square less than or equal to this particular value y. And let's first look at what is the range of y. So if x is between 0 and 1, for non-zero probability density, we must have x between 0 and 1, right? So for non-zero probability density of y, we must also have 0 less than or equal to capital Y less than or equal to 2, because y is 2x square. So just square these and multiply by 2. So 0 square times 2 and 1 square times 2. So this is assuming this value y lies between 0 and 1. Otherwise it's clear. For anything less than 0, this will be 0. And for anything greater than 2, this will be 1, because it's the CDF. Okay, so that part is obvious. We only look at the non-trivial part. So this we assume. And therefore, I can say here that x square x less than or equal to square root of y by 2. Is that right? Normally, I would have to take x lies between negative square root of y by 2 and positive square root of y by 2. But here x is anyway non-negative random variable or positive random variable. So here I'll take only the positive half. But now looking at this and this, this is exactly the CDF evaluated at this point. So this is exactly capital F of square root of y by 2. So I get g of y is this. Now, what is actually f of x? This is integration. So again, assuming x lies between x and 1, between 0 and 1, this is integration of 2x from 0 to x, and that is x square, only in this range. So this will be square root of y by 2, the square, which is y by 2. So g of y is y by 2 in this range. Oh, I wrote 2 here, 1 here by mistake, that is 2. Okay, x is between 0 and 1, y is between 0 and 2. Now, if you're wondering why this equality is not there, that doesn't matter because it's continuous. Okay, so we have g of y is y by 2 for this range, but what we want is a PDF. G of y, small g of y, which is actually the derivative of capital G of y, and so that is d dy of y by 2, which is 1 by 2. Where y lies between 0 and 2. So this is, in this example, what we see is that the matter of finding the PDF of a function of a random variable is not as simple as that in the discrete case. We have to find it indirectly by first finding the CDF of the new random variable and then differentiating it to find the PDF. But if you observe this carefully, this procedure that we have carried out here, most probably we can generalize it, because all we're doing is first we rewrite the given event, the event y less than or equal to y in terms of x, and that gets converted to some evaluation of the CDF of x, and then we differentiate that CDF to get the PDF. So to get the CDF, we are originally integrating the PDF of x, and then we are differentiating that. So if we differentiate and then integrate, they should actually cancel out each other, right? Maybe there is a little bit of transformation happening in between, because this is not exactly the CDF of x as it is. This is a CDF of x evaluated at a different point. That point depends on this function. Because y is equal to 2x square, here when we rewrote this event, we got x less than or equal to square root of y by 2, which is in fact the inverse of this function. If you say y is equal to phi of x here, so if you call this function phi of x, then x is equal to phi inverse of y, which is exactly square root of y by 2. So we are evaluating the CDF of x at phi inverse of small y and then differentiating it. But the CDF itself is the integral. So this should be exactly the PDF evaluated at this point, but not quite, because this was integration with respect to x, whereas over here it is differentiation with respect to y. We are differentiating this with respect to y. So if you differentiate this with respect to x, remembering that y and x are related, not independent. So if you differentiate this with respect to x and then multiply by dx by dy, so by chain rule, then you will get this derivative itself. So this is exactly the PDF of x multiplied by dx by dy. Okay. So let's look at that in general. let x be a continuous random variable, okay, with PDF f of x, and let y equals phi of x, where phi is a monotonic function. So what does monotonic mean? It's either strictly increasing or strictly decreasing. Again, what does that mean? Strictly increasing means if x1 is greater than x2, then phi of x1 is strictly greater than phi of x2. And strictly decreasing is the opposite. If x1 is greater than x2, then phi of x1 is strictly less than phi of x2. Note that this is greater than. We don't invert both of these inequalities. If we do, then that will be the same thing written in a different way. It will not be an opposite of the property, it will be the same property. So strictly decreasing means as the argument or the input value increases, the function value decreases. That's decreasing. And increasing is the function increases when the input increases, and strictly because it does not remain constant at any point. You can have a non-decreasing function, which is something where x1 greater than or x2 greater than x2 implies phi of x1 greater than or equal to phi of x2. It may remain constant or it will increase. So for example, the CDF of any random variable is always a non-decreasing function. Okay. So this is a monotonic function. Note that as an implication of this monotonicity, this function is invertible. So at any point, if x1 is not equal to x2, then definitely phi of x1 cannot be equal to phi of x2, because if x1 is not equal to x2, either x1 is greater than x2 or the other way around, which is just a matter of renaming x1 and x2. So one of these holds, right? So in this case, if it's strictly increasing, then x1 greater than x2 means these are not equal. Here also, if they're strictly decreasing, then also they are not equal. Right? So as an implication of monotonicity, we have invertibility, and that is what we're going to use. The statement of the theorem is, suppose this is the case, then the PDF of y is equal to the PDF of x multiplied by modulus of dx by dy, where it is understood that this is f of x written in terms of y. Okay, so we'll quickly prove this. So again, the general proof also goes along the same lines as what we saw in the example. The CDF of y is g of y, which by definition is probability that y is less than or equal to y. That is probability of phi of x less than or equal to y, where y is a particular value. Now remember, because of monotonicity, I can invert this. So it becomes x less than or equal to phi inverse of y. But this is not always so. It is possible that phi is a decreasing function, right? This is the other possibility. So in that case, the inequality will be inverted. So we'll have x greater than or equal to phi inverse of y. Okay, we'll first deal with this case and then go to this case. And I'll explain why this can happen or how this inequality is reversed in when I discuss that case. So let us first look at this case. So this is the phi is increasing case. Okay, and this is the other case where phi is a decreasing function. Now, what I will write here is just for convenience of notation, I'll write probability of x less than or equal to x, where x is phi inverse of y. Okay, so this is obviously the CDF of x evaluated at this point x. So what we got is g of y is equal to f of x. So now the PDF is obtained by differentiating this. So the PDF of y is g of y, which is, remember, differentiation of the CDF with respect to y. So that is d dy of f of x. Now, obviously, again, remember this is not 0 because this x is actually defined in terms of y. So it's not an independent variable. So this is by chain rule d dx of f of x multiplied by dx by dy, which is f dash of x times dx by dy. Actually, I won't write f dash. You can directly write. What is differentiation of CDF? It is PDF. So it is a PDF of x multiplied by dx by dy. Okay, so this is almost what we have here, only there is a modulus. Is that modulus a problem? No, because remember y is an increasing function of x in this case, in the first case. So if y is an increasing function of x, x is also an increasing function of y when you take the inverse. So this is dx by dy is already positive. For an increasing function, the derivative is positive. Or you can think y is increasing, therefore dy by dx is positive. Dx by dy is merely the reciprocal of that, which is also positive. So this is very well equal to f of x times modulus of dx by dy as required. Okay. Now I'm writing this here because in the other case we get the same thing. So you can probably guess what is going to happen. Over there we'll get minus dx by dy in the same place. Okay. Now, why is this inequality inverted here? So consider the case of a decreasing function. A typical decreasing function would be say y equal to 2 minus 3x. Then if I write y less than or equal to y, it is 2 minus 3x less than or equal to y. So what happens? Minus 3x less than or equal to y minus 2, or x is greater than or equal to 2 minus y by 3, or okay, I'll write first is y minus 2 by minus 3. Remember, when you multiply or divide by a negative number, the inequality gets reversed. Or you can even think of this as taking this term over to this side and this term over to this side. So you get minus 3x on the other side of the inequality, which you are just writing here. Okay, you get 3x on the other side rather, which you're writing in this way, and then dividing by 3. So you get x greater than or equal to y minus 2 by minus 3. So the inequality is reversed. And this is true whenever you have a decreasing function. In fact, that is what the definition says. If you apply phi, the inequality reverses. And so if you apply phi inverse, then also the inequality gets reversed. So this is typical. You can also try with the reciprocal function. So if you take y is equal to 1 by x, that's another decreasing function. In that case also the same thing would happen. Similarly, any other composite functions like y is equal to e to the power of minus x. that is also decreasing function. So anything like that. Whereas y equal to e power x is increasing function. Y equals log x is increasing function. Okay, so this is clear now. Here we get the reversal of the inequality when you go from here to here. Okay, the inequality gets reversed. Now this is not the CDF, but rather it is 1 minus probability of x less than or equal to phi inverse of y, which is 1 minus probability of x less than or equal to x, where again x equal to phi inverse of y, same definition. And this is the CDF, so it's 1 minus f of x. Therefore, the PDF of y is, so remember this is g of y, right? G of y is equal to this. So the PDF of y is again the derivative of g of y, which is now derivative of 1 minus f of x, which is minus d dx of f of x times dx by dy. The d dy of 1 is 0, and d dy of f of x, by chain rule, it is d dx of f of x times dx dy. This minus remains, which is f of x times minus dx by dy, because d dx of f of x is as before small f of x. There's no negative in that. Okay, but this minus I'll group with this, so minus dx by dy. Now in this case, phi is a decreasing function, so dy by dx is negative, or dx by dy is negative. So negative of that is positive. So this minus dx by dy is just another way to take the positive value or magnitude of this quantity, which is exactly this. So even in this case, we get the same thing. So this is equal to this, and this is also equal to this from the two separate cases. Both of these are two different cases according to our assumption of two cases. Both of these are the different cases. Both of them lead to the same answer. That's how you prove this theorem. Okay. So now that we have this, we can apply this whenever we have a monotonic function. Okay. So let's look at some examples. So here you have the PDF x with PDF of x given by 3x square by 2 in this interval minus 1 comma 1, and you're given three different functions. So first is y equal to 2x plus 2. So is 2x plus 2 is a monotonic? Is it a monotonic function? Definitely, it's a monotonically increasing function. Not monotonically increasing, strictly increasing function. A monotonic means strictly increasing or strictly decreasing. So this is a strictly increasing function. Phi of x is this 2x plus 2. Okay, the phi of x in the theorem is just 2x plus 2 in this example. So we have y equal to 2x plus 2. So what we do first is write x in terms of y. So x is equal to y minus 2 divided by 2. Okay, so dx upon dy is equal to 1 by 2. So this we write for the values. So I'll write small x and small y. So f of x is given to be 3x square by 2 in the interval minus 1 comma 1. So g of y is f of x written in terms of y multiplied by the modulus of dx by dy. F of x written in terms of y is 3 by 2 x square. X again here is y minus 2 by 2. So y minus 2 by 2 whole square times dx by dy is half. Now what is the range of y? So if minus 1 less than or minus 1 less than x less than 1, then we have y equals 2x plus 2, right? So here multiplying by 2 and adding 2, you will get 0 less than y less than, here multiplying by 2 and adding 2, we get 4. So in the range 0 less than y less than 4. This is the answer. Of course, you can simplify this a little bit and write it as 3 by 16, I believe. Yeah, 4 times 4, y minus 2 the whole square for y between 0 and 4. And the second example, z equal to x cube. So x is equal to cube root of z, or I'll write that as z to the power 1 by 3. And so when you differentiate x with respect to z, you'll get 1 by 3 z to the power of minus 2 by 3, that is 1 by 3 z to the power 2 by 3, with z to the power 2 by 3 in the denominator. And also minus 1 less than x less than 1 implies we require this also. So minus 1 less than x less than 1 implies x cube also lies between minus 1 and 1. So that is z lies between minus 1 and 1. So then it's just a matter of substituting. Let's say h of z is, I'm not rewriting the formula. So f of x in terms of z. So f of x is over here, x square. What is x? Z cube. Z to the power 1 by 3. Right? This times modulus of dx by dz, which is this under modulus. So here we had half, so we didn't actually have to take modulus here in the previous one, right? Here we'll write modulus, but again, as we'll see, you can remove the modulus right away because it is z to the power of 2 by 3. So that means you're actually taking the square of z and taking a square cube root. So this will cancel out any sign that z has. Z actually can vary from minus 1 to 1. So if it was z to the power 1 by 3, for example, you have to keep the modulus there. But here it is 2 by 3. So the sign does not matter. It will always become positive. So we can actually in the next step remove the modulus. But here let me write. This is not something you should forget. So you write it in every step after this. Now here you have 3 and 3 will cancel out. And this 2 remains. So z to the power 1 by 3 whole square is z to the power 2 by 3. And here again you have z to the power 2 by 3. So in fact those will also cancel out. And you get just 1 by 2. Right? So in fact, z here has a uniform distribution in this interval. You can immediately see this is a valid PDF because it is 1 by 1 minus minus 1, which is a valid PDF for the uniform distribution. So actually z has uniform distribution if x is given by this PDF and z is equal to x cube. Now in the third case, we rewrite the question. U is equal to x square. Again, let me rewrite the PDF. All right. So u equal to x square implies x is equal to square root of u. But this is not a monotonic function because x is going from minus 1 to 1. If x was only between 0 and 1, then it would be monotonic, but here it's not. So you cannot actually use that theorem as it is here. We can use a modified form or a generalization of the theorem in this special case, but let us look at it without that first. So it is not really correct to write x equal to square root of u. That is true only in one half. Only for x greater than 0, this is true. For x less than 0, x is equal to minus square root of u. So this is actually, the inverse is not one function, but two different functions in two different ranges. Okay, so what we can do here is, before going to the generalization, again start with the CDF, because that's the only thing we know. So I'll take K to be the, so I've used G and H here. So I'll take K to be the, small k to be the PDF, and capital K to be the CDF of U. Let me write K of U is probability of U less than or equal to small u. Again, that is probability of x square less than or equal to u. But now this comes out to be probability of minus square root of u less than or equal to x less than or equal to square root of u. If you recall an earlier example, we took only one part of it because x was between 0 and 1 over there. Here x is between minus 1 and 1. So this is also a possibility with non-zero probability. Can we write this in terms of CDF? If it was only this part, then it is just capital F of square root of u. But this is also there. Nevertheless, we can write it in terms of CDF as f of square root of u minus f of minus square root of u. Because remember, this is probability of x less than or equal to square root u minus probability of x less than or equal to minus square root of u, which is exactly this. And now to find the PDF, so without actually integrating and finding it out, to find the PDF of u, that is k of u, you have to differentiate the whole thing. Okay. So by chain rule, this will be f dash of square root of u, which is small f of square root of u, times derivative of square root of u, which is 1 by 2 root u, minus f dash of minus square root of u, which is f of small f of minus square root of u, times the derivative of minus square root of u, which is minus 1 by 2 root u. Now you can see this minus cancels out. So actually you get 2 times the first term, because the okay, not exactly, because this is there, right? So let me write that first. You get sorry, you get 1 upon 2 root u f of square root of u plus f of minus square root of u. But additionally in this problem, this function is symmetric. This function is symmetric in this interval. So f of plus square root of u and f of minus square root of u are both equal to, so let me write it here, f of root u is equal to f of minus root u is equal to 3u by 2. So here you will just get 3u by 2 plus 3u by 2. So the final answer will be 3 by 2 square root of u, where if u is equal to x square and x is between minus 1 and 1, u is between 0 and 1. So this is the PDF in this case. Here we have to first get the CDF involved in this way. right? We start with the CDF of u, but that turns out to be f of square root of u minus f of minus square root of u. So you can see that this is we have not used any particular property of x here. This is always going to happen. If u is equal to x square, this will always happen. And if u is some other function of x, it will differ. But if u equal to x square, no matter what is a PDF of x, this is what is always going to happen, provided you have x taking both negative and positive values. So this part is general. And after that, when you differentiate it, again, this part you will always get if x has a symmetric PDF, if x has a symmetric distribution. So in the next problem, you will see that over here in this second part, the same thing will happen. Although it's not a squaring function, this is also a symmetric function, symmetric non-monotonic function. Okay, this function cos of pi x by 2 has it's not injective. It takes the same values for plus x as well as minus x because it's an even function, which makes it symmetric and non-monotonic. And this x has uniform distribution, so that is also a symmetric distribution. So whatever happened in the previous problem will also happen in this part. Okay, let's look at the first one. The first one is again a simple application of the earlier theorem, because recall that the tan function is here when you have x between minus 1 and 1. Tan of theta, if x is between minus pi by 2 and pi by 2, looks something like this. Okay, these are asymptotes, that doesn't matter. So tan of theta when theta is between minus pi by 2 and pi by 2 is this, and therefore here tan of pi x by 2 when x is between minus 1 and 1 is the same curve essentially, right? Only scaled differently, but it's the same curve. So this is a monotonically increasing function. This is a strictly increasing function and therefore is monotonic. So we can write the PDF using the earlier theorem. So first of all, what is f of x? It's given only that x has a uniform distribution. The PDF is not explicitly given. But recall that the PDF of a uniform distribution is f of x equal to 1 by b minus a when x is between a and b. So in this case, a and b are minus 1 and 1. And so 1 by 1 minus minus 1 is 1 by 2. So this is the PDF of x. And therefore the CDF, the PDF of y, let's take y equal to the given function. So y is equal to tan of pi x by 2, since the name is not given in the question. The PDF of y is PDF of x multiplied by modulus of dx by dy. Now, since x is equal to 2 by pi tan inverse of y, we have dx by dy is equal to 2 by pi times 1 plus y square. So this is half of 2 by pi times 1 plus y square. But what is the range of y? As x goes from minus 1 to 1, y is tan pi x by 2. So tan of minus pi by 2 is minus infinity, and tan of plus pi by 2 is plus infinity. So y goes from minus infinity to plus infinity. So if you don't write anything, that is a meaning, right? So here it is just 1 by pi times 1 plus y square. And if you recall, this is actually the PDF of Cauchy's distribution. It's not essential to write this in the answer. This is just an observation. So now in the second case, the PDF is the same. F of x is half in the range -1 to 1. The same random variable for this also. But now y is equal to cos of pi x by 2. And if you recall the graph of cos x, if theta is between minus pi by 2 and pi by 2, cos theta graph is basically this, and this is 1. So here, when x is -1, cos of pi x by 2 will be cos of minus pi by 2, which is this. So this will be -1. Similarly, this will be 1. Okay. So here we have x is equal to 2 by pi cos inverse of y, and as x goes from -1 to 1, y will go from 0 to 1 and back to 0. So actually y lies between 0 and 1. Again, you can include the equal to or not. It's continuous, so it doesn't matter. But now the problem here is this is not a strictly increasing or strictly decreasing function. So it's not a monotonic function. It is increasing in this part and decreasing in this part. But it is symmetric. So as before, what we will get is g of y will be f of x plus f of minus x times modulus of dx by dy. So if you observe the what we did in the previous problem, this is exactly what we got, where x is such that phi of x and phi of minus x equal to y. So remember, this is a non-monotonic function, and in this particular case, it is symmetric about the origin, symmetric about the y-axis rather. So what happens is phi of x and phi of minus x both will be equal to the same value, because it's actually an even function here. So both of these will be the same value. So when you take inverse, as we did in the general case of the theorem, we won't get one value but two values. So x and minus x are the two different inverses of y. And so if you take any such x, then corresponding to that y, you will get two cases which will split into two probabilities or two evaluations of the CDF, one at x and one at minus x, and you're subtracting them. And then when you differentiate, you will get basically this. The extra minus from here will cancel out. So actually it is f of x times dx by dy minus dx by dy times f of minus x. Well, minus of dy of minus x times f of minus x. So this is what you will get. Again, you write these in terms of y. So here there is no problem because f of x is half. So that's not a problem. You can just write half plus half. And what is dx upon dy? It is just derivative of this, which is 2 by pi minus square root of 1 minus 1 by square root of 1 minus y square. So adding these up is 2 by pi 1 by square root of 1 minus y square for y between 0 and 1. The modulus cancels out the minus. And it's easy to verify that this is a valid PDF. So whatever we've done here is correct. So that is what happens in this case. If you have any random variable where this kind of symmetry is not there, So this, in order for this to work, the symmetry has to be there in the PDF as well as the function you are taking of the random variable. If the symmetry is not there, then the only general thing that works is finding the CDF very carefully and then differentiating it. So it may happen that there is a more complicated function or distribution, and you have to split it into different intervals and find the CDF in each different interval. These are the simpler cases, in which case you can apply these theorems.